So in year 8, in half term 4, you'll be learning about our physical world. One of the most important parts is relief, which is the height and shape of the land. And relief is very different at extremes, so very high land, very low land around the world. We can also think about extremes and the world in terms of longitude and latitude. I like to think of latitude as flatitude because they are flat lines across or around the globe. The most important one is at 0 degrees latitude, the equator, but we also have the Tropic of Cancer and the Tropic of Capricorn at 23 degrees, 23.5 degrees north and south of the equator. The most important lines of longitude go down the Earth, is the prime meridian, which is 0 degrees in terms of longitude. In terms of a world of extremes, we have extremes of mountains. So this is Mount Everest, 8,848 meters tall. The river Ganges in India, a really spiritually and religiously important river, and also our ocean. So this is a sea lion in California enjoying some seagrass.
Lovely. So on the board we can see what the world would look like if all the water was taken out of the oceans. The relief of the surface of the sea floor is not perfectly flat, and as you can see here, in between the continents of North America, South America, Europe and Africa, there is a mountain range called the Mid-Atlantic Ridge that runs down the centre of the Atlantic Ocean, and this is because the sea floor is spreading. The reason this happens is because the surface of the Earth is broken into plates. If we look at this diagram, this shows the 4 sections of the Earth. You've got the inner core, centre of the Earth, solid iron, about 5,500 degrees. We've got the outer core, which is liquid iron. We've got the mantle, which is semi-molten rock, and the crust. And the crust floats on top of the mantle, and convection currents moving in the mantle cause the crust to move in different directions. So here we can see what the Mid-Atlantic Ridge would look like if we drew a red line down the Atlantic Ocean. This photograph is an aerial photograph of the Mariana Trench. So this is the deepest point in the world's oceans, and it is deeper than Mount Everest is tall. If we look at this map, we can see the world split up into these tectonic plates that I mentioned. We have continental plates, which is basically land, which are thick, less dense and can't be destroyed. And under the ocean, we have oceanic crust, which is thinner but more dense, and it is constantly being destroyed and replaced. For example, if we look at the Nazca plate, it is converging with the South American plate. The Nazca plate is oceanic, so it sinks below the South American plate, getting destroyed, and that is why you get chains of volcanoes and mountains here. Whereas on the western side of the Nazca plate, magma and molten lava is being released and the plate is growing. Now, there are 3 types of plate margin. The first plate margin is a conservative margin, sometimes called a strike-slip margin. And what happens here is plates are moving alongside each other. Pressure builds up, which is eventually released during an earthquake. You also find fault lines. People like to live here because it can give them access to water from below the Earth's surface. The next example of a plate margin is the constructive plate margin. Constructive, like it says on the tin, is when new land is created. 2 plates move away from each other or diverge. Magma is released as lava, creating new land, and this is why we've got underwater volcanoes and the mountain range at the Mid-Atlantic Ridge. The final plate margin is a destructive plate margin. Here we can see 2 plates coming towards each other or converging. The dense oceanic plate sinks below the continental plate. The plate melts, a magma chamber is formed, and you will find here steep-sided volcanoes. Another feature that we can find is where the plates meet, there is a deep trench called an ocean trench, like the Mariana Trench that I mentioned about a minute ago. In terms of measuring tectonic hazards, we can use the Richter scale. A Richter scale is a logarithmic scale, and the further you go up, the higher the amount of energy is being released by a particular earthquake. This map shows the global distribution of earthquakes. The red dots are where earthquakes happen. As you can see, overwhelmingly, most earthquakes happen at or around plate margins. However, some of them are more sporadic. An example of an earthquake we can look at is the 2015 Kathmandu Earthquake that happened in Nepal. As a result of the Indian plate crashing into the Eurasian plate, it had devastating effects because of the low levels of development, buildings collapsed and many people died. Another example of a tectonic hazard, this time in a HIC, a high-income country, is the Japan 2011 earthquake, which triggered a tsunami. As you can see, the sea defences which were here were overrun, the water rushed into land, and this led to the death of around 20,000 people. And
the tsunami generally affected the east coast of Japan, so particularly the cities of Sendai in Miyagi Prefecture. So a tsunami wave of 30 metres covered most of the east coast, led to huge amounts of damage, social and economic impacts. Here you can see the city of Sendai before and after the tsunami and the wave of destruction and debris that it left. We can also think about the structure of a volcano. So volcanoes are ordered or constructed in layers. Each one is the product of an eruption. We have the main vent, which is fed by the magma chamber, where the magma rises up to the surface. We can also have volcanic bombs shooting out and falling by the side of the volcano, or pyroclastic flows, which are really hot clouds of gas and smoke and rocks that flow down the mountainside. An example is the 2021 eruption of Nyiragongo in the Democratic Republic of Congo, one of the poorest LICs in the world, caused massive damage to infrastructure, and 400,000 people were left in refugee camps. Quite often in India in the summer you will see this image because of the monsoon. Now, a monsoon is just a seasonal change in wind direction, and in India, the seasonal change in the summer brings water from the Indian Ocean over the continent and drops massive amounts of rainfall in India. An example, flooding, extreme flooding, loads of economic and social impacts. However, people in India have adapted to the monsoon to ensure that their lifestyle can continue. Tropical storms. Tropical storms are essentially formed by evaporation of warm seawater at 27 degrees Celsius, usually around the tropics, and they spin and collect more energy because they're near the equator, and there is more Coriolis force there. This is what a tropical storm looks like. In the centre you've got an eye where you would have calm conditions. The eye wall around the centre would have the most damaging conditions, so heavy rain and really strong winds, and we also have rain bands around the edge of the storm as well. This is the track of Hurricane Irma, which happened in 2017. It tracked northwest through the Caribbean, hitting islands such as the US Virgin Islands, Puerto Rico, before hitting Cuba, and then eventually Florida in the United States. This is some damage from Florida that you can see, even in a HIC, massive damage to infrastructure. So the three tasks: you could either do an annotated diagram of the three types of plate boundaries, a report that summarises the causes, effects and responses to a tropical storm in the last 10 years, or you can think about a fact file about a recent volcanic eruption, again in the last 10 years, causes, effects and responses again. Don't forget to upload it to Teams.